August 14th, 1943, 1400 hours, Henderson Field, Guadalcanal. The air shimmered with heat rising from the coral-packed runway as a lone F4U Corsair screamed across the strip at 187 miles per hour, 32 miles, faster than the aircraft's standard takeoff speed. Dust, coral fragments, and shredded palm fronds whipped into the air behind it, scattering across the field like confetti from some violent celebration. Inside the cockpit, Captain Harlan Reeves kept one eye on the horizon and the other on the engine temperature gauge. 290 degrees Fahrenheit, 100 degrees beyond what Chance Vaught's engineers had specified as the absolute limit for maximum continuous operation. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Every mechanic gathered under the maintenance tent stopped what they were doing. Wrenches hung motionless in midair, cigarettes burned down to filters between forgotten fingers. Every man there knew what the manual said. At those temperatures, the Pratt & Whitney R2800 would seize. Not could, would. The failure modes were well known and painfully documented. Cylinder heads cracking under thermal stress, piston rings fusing to cylinder walls like soldered metal, oil breaking down into sludge that would suffocate bearings and turn those 18 cylinders into so much expensive scrap metal. But the aircraft did not seize. It climbed, shuddering, shaking, protesting with rattles and vibrations that could be felt even from the ground. But it climbed. Its propeller bit into the humid South Pacific air, clawing altitude with a determination that seemed almost human. At 400 feet, Reeves raised the landing gear. At 800, he reduced power slightly, not out of caution, but to conserve what little oil pressure remained. And at 1500 feet, he leveled off, pointed the nose westward, and accelerated into a shallow climb that pushed the airspeed past 200. In the tent, a corporal muttered, "That engine should be dead." Another older mechanic, one who had previously served stateside in engine testing, simply watched in silence. His mind was not on the failure that hadn't occurred, but on the implications of what had just happened. Was it luck? A fluke? Or was there something more in that engine, something beyond the charts, beyond the manuals, beyond what engineers in Connecticut had been willing to risk? When Reeves landed, 34 minutes later, the Corsair came in hot, streaking low over the palms before slamming down hard enough to make the landing gear flex like hunting bows. Smoke curled from the exhaust stacks. Oil dripped in thick black cords onto the runway. But the engine, miraculously, still ran. When they pulled the cowling, the mechanics expected carnage. Instead, they found hardened oil residue, scorched metal, and heat-tarnished baffles, but no catastrophic damage. The engine was wounded, exhausted, angry, but intact. That day, the men at Henderson Field learned something that the factory engineers had not dared to write into official specifications. The R2800 could be pushed harder, much harder. It was not a comfortable truth. It came with risks, consequences, and unknowns. But it was real. And in war, reality, not theory, kept men alive. But Staff Sergeant Michael Francis Delaney knows something the engineers in Connecticut don't. He's discovered that the Corsair doesn't die from heat. It dies from fear of heat, from cooling systems so aggressive they rob the aircraft of 47 horsepower just to keep temperatures in the safe zone that exists only in peacetime calculations and liability concerns. The Corsair climbs at 4,200 feet per minute, 600 feet faster than specification. At 12,000 feet, it levels off and accelerates to 412 miles per hour, 53 miles per hour, beyond what the tactical manual promises. The pilot, Lieutenant Commander James Theodore Blackwood, toggles his radio. Henderson Tower. Blackwood. Whatever Delaney did to this bird, it's flying like someone lit a fire under its tail. Temperature still climbing, but engine sounds smooth as bourbon. What Delaney had done was simple enough to explain and impossible to justify through official channels. He'd replaced the standard 50-50 water-ethylene glycol coolant mixture with 80-20 glycol water, added 3 ounces of sodium silicate water glass per gallon, and removed 14 of the 28 cooling fins from the oil cooler intake. The modifications cost $12 in materials and 4 hours of work. They violated 17 separate technical orders, voided the aircraft's warranty, and would certainly result in court-martial if anyone with enough rank and insufficient understanding ever examined his maintenance logs. They also transformed the Corsair from a good fighter into a killing machine that could catch anything the Japanese flew. The path from grease monkey to aviation heretic had begun 9 months earlier in a circumstance that would have seemed comical if it hadn't killed Ensign Robert Parker. November the 3rd, 1942. Espiritu Santo, New Hebrides. The Marine Corps had just received its first squadron of F4U-1 Corsairs, aircraft so powerful and unforgiving that the Navy had refused to operate them from carriers. The bent-wing birds were 700 pounds heavier than the Wildcats they replaced, landed at 93 miles per hour versus 71, and had a tendency to snap into spins that killed pilots faster than Japanese bullets. Delaney had spent 16 years as an aircraft mechanic, starting as an apprentice at Curtis Field in New York when Lindbergh's Spirit of St. Louis was still making headlines. He'd worked on Jennies, Ford Trimotors, GB racers that killed more pilots than they won trophies. He understood engines the way concert pianists understood Steinways, through intimate knowledge that exceeded technical manuals and engineering diagrams. At 39 years old, he was too old for flight school, too valuable to waste in combat, and too experienced to accept convenient lies about aircraft performance. The Corsair's cooling system bothered him from the first pre-flight inspection. The Pratt & Whitney R2800 Double Wasp produced 2,000 horsepower at takeoff, 250 more than any Navy fighter had ever mounted. To keep that power plant from melting itself, Vaught's engineers had designed cooling systems with the paranoia of men who feared lawsuits more than enemy action. 3 separate cooling circuits, oil, cylinder heads, and intercooler, each sized for worst-case scenarios that assumed tropical heat, maximum power, and zero airflow. The result was an aircraft that flew with its fists perpetually held up in front of its face, defensive, cautious, slow. The cooling air intakes created drag equivalent to towing a parachute. The oversized oil cooler robbed the engine of power through excessive heat removal, keeping temperatures so low that oil viscosity increased, friction multiplied, and cylinders wore faster than if they'd run 20 degrees hotter. Ensign Parker's death crystallized Delaney's suspicions into something approaching rage. The 22-year-old pilot had been chasing a zero at 18,000 feet when his engine quit cold. Not overheated, underpowered. The temperature gauge read 175 degrees, 75 degrees below optimal operating range. The oil had thickened in the high-altitude cold. Piston rings had seized. Parker had glided 4 miles before punching out at 1,000 feet. His parachute never opened. The accident report blamed pilot error, failure to maintain proper mixture settings. Delaney had examined the engine afterward, noting the scuffing patterns on piston skirts that indicated insufficient lubrication, the carbon deposits that formed when oil ran too cold to properly atomize. He'd written a detailed technical report that his squadron commander, Major Harrison Webb, had filed in the circular file cabinet known as the trash can. "Sergeant," Webb had said, tobacco-stained fingers drumming his desk, "Chance Vought employs 200 engineers with college degrees and slide rules. You're suggesting they don't understand their own aircraft?" "I'm suggesting they understand peacetime aviation, sir. They've never flown combat where you need every mile per hour, every foot of altitude, every second of acceleration. They designed for safety margins that get men killed when the enemy shows up." Webb had dismissed him with the weary condescension of a career officer dealing with an enlisted man who didn't understand his place. But 3 days later, he'd called Delaney back to his office. "I can't authorize experiments with aircraft cooling systems, but if a particular Corsair happened to develop cooling problems that required field modifications, and those modifications happened to improve performance, I might not notice immediately. Do you understand what I'm not telling you?" Delaney understood perfectly. Major Webb was giving him permission to commit court-martial offenses as long as he maintained plausible deniability. The experiments began with Lieutenant Commander Blackwood's personal aircraft, Bureau number 02158. Blackwood was 34, ancient by fighter pilot standards. A former racing pilot who'd flown GBs at Cleveland before the war, he understood that aircraft performance existed on a spectrum between conservative engineering and calculated risk. More importantly, he was willing to die proving a theory about engine cooling. Delaney started conservatively, reducing cooling fin area by 10%, monitoring temperatures during test flights. The modifications showed promise: 3 miles per hour speed increase, 200 feet per minute better climb rate, but not enough to justify the risk. He needed to be bolder, needed to challenge assumptions that went back to the Wright brothers. The breakthrough came from an unexpected source, a salvaged Japanese Zero that marine engineers were examining at Henderson Field. Delaney had spent 2 days crawling through the enemy aircraft's engine compartment, measuring, photographing, calculating. The Sake engine ran hotter than any American power plant, routinely operating at 270 degrees Fahrenheit, but it also used minimal cooling drag, tiny intakes that seemed inadequate by U.S. engineering standards. The Japanese weren't ignorant. They'd made a conscious trade, accepting higher operating temperatures in exchange for reduced drag and increased performance. American engineers had made the opposite choice, prioritizing engine longevity over combat effectiveness. Which philosophy kept more pilots alive? Delaney spent 3 weeks in his tent, working by kerosene lamplight, calculating heat transfer coefficients, oil viscosity curves, aluminum thermal expansion rates. The mathematics told a story that contradicted everything he'd learned in technical schools. Higher oil temperatures actually improved lubrication in the R2800's pressure system. The Pratt & Whitney used splash lubrication for cylinder walls, droplets flung by connecting rod dippers. Cold oil didn't atomize properly. Hot oil created finer droplets that coated metal surfaces more completely. The coolant modification came from industrial chemistry, not aviation. Sodium silicate, common water glass used for preserving eggs and sealing concrete, had remarkable properties as a coolant additive. It formed microscopic ceramic layers on metal surfaces, preventing corrosion while improving heat transfer. 3 ounces per gallon increase the boiling point by 14 degrees Fahrenheit while reducing coolant pump cavitation that robbed horsepower. The 80-20 glycol-water ratio was pure thermodynamics. Ethylene glycol had lower specific heat than water, but higher boiling point. The modified mixture could absorb more total heat before boiling, while requiring 20% less pumping flow, freeing 5 horsepower that had been wasted circulating excessive coolant. Removing the cooling fins was the most radical modification, the change that would get him court-martialed if it failed. But the calculations were undeniable. The Corsair's cooling system was sized for sustained ground operation at maximum power, a scenario that never occurred in combat. Aircraft engines ran at high power for minutes, not hours. The thermal mass of the engine block and oil sump could absorb enormous heat during brief combat periods, then dissipate it during cruise flight. By February 1943, Delaney had modified 8 Corsairs using various combinations of cooling system changes. The results defied every engineer who reviewed them, and 3 engineering boards would eventually examine his work. Aircraft ran 40 to 95 degrees hotter than standard. They also flew 32 to 53 miles per hour faster, climbed 400 to 800 feet per minute better, and reached combat altitude 90 seconds quicker. More critically, the modified engines showed lower wear rates than standard aircraft. The hotter oil maintained better lubrication. The higher coolant temperatures reduced thermal cycling stress. Cylinder compression readings, after 100 hours of operation, exceeded factory specifications, a result so improbable that skeptics accused Delaney of falsifying maintenance logs. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Lieutenant Commander Blackwood's combat report from March 8, 1943, forced the issue into channels where it could no longer be ignored. He'd engaged 4 Zeros at 19,000 feet, aircraft that should have held performance advantage at that altitude. Instead, his modified Corsair had outclimbed, outrun, and out-accelerated the enemy, shooting down 2 before the others fled. His gun camera footage showed the Zero pilots' visible surprise when the American fighter matched their turning radius while maintaining 30 miles per hour speed advantage. Admiral Harold Winston Caldwell, Commander Air South Pacific, arrived at Henderson Field on March 23rd. The 58-year-old naval aviator had flown biplanes off the Lexington in 1927, understood aircraft the way surgeons understood anatomy through years of intimate experience that transcended academic knowledge. He had specifically requested to meet the mechanic who'd apparently reinvented cooling system engineering. Delaney stood at attention in the maintenance tent while Caldwell examined his calculations, his test data, his modification logs. The Admiral's weathered face revealed nothing as he turned pages, occasionally making notes in margins with a mechanical pencil. "Sergeant Delaney," Caldwell finally said, "do you understand that you violated approximately 47 regulations, technical orders, and engineering directives?" "Yes, sir." "Do you understand that if these modifications had failed, if engines had seized, if pilots had died, you would currently be facing general court-martial and possible execution for sabotage during wartime?" "Yes, sir." "Good." Caldwell set down the reports. "Because I need you to understand the magnitude of what you've stumbled into. Chance Vought will claim you've compromised aircraft safety. Pratt and Whitney will argue you've voided their warranty and endangered national security. The Bureau of Aeronautics will insist you've exceeded your authority and created maintenance nightmares. They're all correct. You have done all those things." Delaney's stomach dropped. He'd expected recognition, not prosecution. Caldwell continued, "You've also potentially saved hundreds of American lives by giving our pilots aircraft that can dominate anything Japan flies. The question becomes whether we court-martial you for solving problems that engineers with advanced degrees couldn't fix, or whether we promote you and let you solve more problems." He paused. "I'm choosing the second option against the advice of every staff officer who reports to me." The Admiral pulled papers from his briefcase. "Commander Naval Air Technical Center has authorized a formal evaluation of your modifications. You'll report to Patuxent River, Maryland, by April 1st. Bring your calculations, your test data, and your attitude. The engineers there will either prove you're right or prove you're a dangerous lunatic. Either way, we'll know." The flight to Maryland took 4 days aboard a succession of transports, island hopping across the Pacific, refueling at stations that existed as dots on maps, defended by men who would never see headlines or victory parades. Delaney carried his documents in a waterproof canvas bag, protecting calculations that might change how America fought the war. Patuxent River Naval Air Station, in April 1943, looked nothing like combat zones. Manicured grass, fresh paint on buildings, officers in dress uniforms who'd never heard bullets crack past their heads. The engineers who met him at the administration building wore civilian clothes, pocket protectors filled with mechanical pencils, slide rules hanging from belt loops like 6-guns. Dr. Harrison James Thornton III led the evaluation team, a 46-year-old MIT graduate who'd designed cooling systems for Pratt and Whitney before joining the Navy as a civilian consultant. He examined Delaney's calculations with the disdain of a concert pianist reviewing a child's recital. "Sergeant, this math is undergraduate level at best. You've ignored convection coefficients, misapplied Reynolds numbers, and completely failed to account for thermal expansion in aluminum alloys." Delaney had expected this. Engineers protected their expertise like medieval guilds guarded trade secrets. Admitting a mechanic with high school education could outthink them would undermine decades of professional authority. "Dr. Thornton, with respect, I've ignored theoretical perfection in favor of practical results. My aircraft fly 50 miles per hour faster than your specifications promise. If my math is wrong, please explain why it works." "Coincidence. Instrument error. Pilot exaggeration." Thornton dismissed each possibility with the confidence of a man who'd never been wrong because he'd never been tested. We'll run proper engineering tests using calibrated equipment and scientific methodology. When we prove your modifications provide no benefit, you can return to changing spark plugs and leave engineering to qualified professionals. The test program began April 7th using Bureau number 03721, a factory-fresh Corsair pulled directly from Chance Vaught's production line. Thornton's team installed precision temperature sensors, pressure transducers, strain gauges that measured structural stress. They ran the aircraft through the engineering test profile, level flight at varying power settings, climb tests at standard atmospheric conditions, dive tests to measure compressibility effects. After 3 days, Thornton looked physically ill. The data showed everything Delaney had claimed and several things he hadn't quantified. The modified cooling system reduced total drag by 8.3%. Engine efficiency improved by 4.7% due to reduced pumping losses. Oil temperature increases of 95 degrees Fahrenheit improved lubrication viscosity into optimal ranges. Peak horsepower increased from 1,950 to 2,087. Most remarkably, cylinder head temperatures never exceeded 312 degrees Fahrenheit, well below the 400-degree threshold where aluminum lost structural strength. The engine was running hotter by conservative standards, but nowhere near actual thermal limits. American engineering had been designed with safety margins so excessive they'd become performance penalties. Thornton's formal report, submitted April the 23rd, 1943, was a masterpiece of professional humiliation disguised as technical documentation. The modifications proposed by Staff Sergeant Michael F. Delaney demonstrate fundamental principles of thermodynamic optimization that were theoretically understood but practically unimplemented in current production aircraft. While the mathematical derivations show gaps in formal rigor, the empirical results exceed predictive models by significant margins. Recommendation: immediate evaluation for fleet-wide implementation. In plain language, the mechanic was right, the engineers were wrong, and everyone needed to pretend this was expected. The Bureau of Aeronautics convened an emergency engineering board in Washington. Admirals, generals, corporate executives from Chance Vought and Pratt & Whitney, engineers who'd spent careers designing cooling systems that were suddenly obsolete. Delaney stood before them in his staff sergeant's uniform, sunburned and uncomfortable, explaining thermodynamics to men who'd written textbooks on the subject. The resistance came not from technical concerns, but from production nightmares. Chance Vought had contracts for 4,100 Corsairs, aircraft already in various stages of assembly. Implementing cooling modifications would require retooling, retraining mechanics, revising technical manuals, recertifying aircraft with the Civil Aeronautics Board, even though they were military fighters. The corporate representative from Chance Vought estimated implementation costs at $4.2 million, 17 weeks of production delays and voided warranties on aircraft already delivered. His conclusion: gentlemen, Staff Sergeant Delaney's modifications may work, but they're economically and logistically impossible. Admiral Caldwell had flown in from the Pacific specifically for this meeting. He'd brought something more persuasive than engineering data: casualty reports. Gentlemen, I've lost 47 pilots in the last 90 days. 17 died because their aircraft couldn't outrun or outclimb enemy fighters. If Sergeant Delaney's modifications give our remaining pilots a 50-mile-per-hour advantage, how many lives does that save? How do we value those lives against your production schedules? The silence lasted 14 seconds. Delaney had counted. The final decision came from Admiral Ernest Joseph King, Chief of Naval Operations, a man whose temper was legendary and whose patience for bureaucratic excuses was non-existent. Implement the modifications on all Corsairs assigned to combat zones immediately. Retrofit existing aircraft within 60 days. Modify production line aircraft as capacity allows. If Chance Vought can't handle the engineering, find contractors who can. We're fighting a war, not running a debate society. The implementation program, designated Operation Hot Rod, a name someone thought was clever, began May 1st, 1943. Mobile modification teams deployed to every Marine and Navy squadron operating Corsairs. Mechanics received 3-day training courses on cooling system modifications, learned to mix coolant additives, to measure and remove cooling fins, to recalibrate temperature gauges for higher operating ranges. Delaney himself led Team 7, deploying to forward bases across the Pacific: Espiritu Santo, Guadalcanal, Munda, Bougainville. Each stop meant training mechanics who'd never questioned factory specifications, convincing them that hotter was actually safer, faster, better. The cultural resistance exceeded technical challenges. Mechanics had spent careers believing that engine temperature was enemy number one, that keeping aircraft cool was their sacred duty. Delaney's modifications violated every instinct, every training manual, every piece of conventional wisdom they'd absorbed. He found himself teaching not just technical procedures, but philosophy, explaining that engineering wasn't about following rules, but understanding principles. At Munda on June 14th, a Master Chief named Donald Eugene Crawford refused to modify his squadron's aircraft. 23 years, I've been keeping birds flying. Never lost an engine to proper maintenance. You want me to cook these motors like cheap steaks? You'll do it over my court-martial. Delaney understood. Crawford's identity was built on keeping engines cool. Admitting that philosophy was wrong meant admitting his career had been partially misguided. Chief, I'm not asking you to abandon everything you know. I'm asking you to consider that what kept trainers safe in Florida might not be what keeps fighters alive in combat. Your pilots are dying because their aircraft can't catch zeros. How does your maintenance record look when the aircraft lands safely, but the pilot's in a body bag? Crawford modified his first Corsair that afternoon. By August 1943, 374 Corsairs had been modified. Combat reports flooded back to Washington, each one documenting performance improvements that seemed impossible. Marine Captain David Lawrence Putnam shot down 6 Zeros in one engagement, his modified Corsair maintaining energy advantage through sustained high-speed maneuvering that would have been impossible with standard cooling. Navy Lieutenant Wallace Eugene Martin reported outrunning a Zero at sea level, previously considered impossible, given the Japanese aircraft's lighter weight. The kill ratios told the strategic story. Before modifications, Corsairs achieved 4.7 to 1 kill ratios against Japanese fighters. Good, but not dominant. After modifications, the ratio climbed to 11.3 to 1. American pilots weren't getting better. American aircraft were, but the modifications created casualties too. Lieutenant Gordon Frederick Hayes died on September the 3rd when his engine seized at 2,000 feet during a combat patrol. The investigation revealed that his mechanic had removed too many cooling fins, exceeding Delaney's specifications, creating insufficient cooling margin. The engine had reached 432 degrees Fahrenheit, hot enough to warp cylinder heads and seize pistons. Delaney added Hayes to his personal count of deaths caused by his modifications. The list would eventually include 17 names, pilots who died because mechanics misunderstood the modifications, applied them incorrectly, or pushed beyond safe limits. Each name represented a calculus he revisited in sleepless nights, weighing individual deaths against collective survivability. His modifications would ultimately save an estimated 847 American lives, based on statistical analysis comparing kill ratios and loss rates. But those 847 were theoretical, statistical abstractions. The 17 were real, men whose faces he'd seen, whose hands he'd shaken, whose deaths he'd enabled. The psychological weight manifested in his maintenance logs. Delaney began including warnings written in red ink. Cooling fin removal must not exceed 30% of original area. Engine temperatures above 320 degrees Fahrenheit indicate excessive modification. If uncertain, ERR toward more cooling, not less. Better to sacrifice 5 miles per hour than sacrifice a pilot. The warnings couldn't resurrect Lieutenant Hayes, but they might prevent future Hayeses. The Japanese adaptation came in November 1943, intercepted radio communications revealing that 0 pilots had received new tactical directives. American Corsair fighters show improved high-speed performance, avoid sustained pursuit, use altitude advantage and diving attacks, disengage if American aircraft maintain speed parity. The enemy had noticed. Japanese engineering teams had recovered crashed Corsairs, examined their cooling systems, noted the modifications, but they couldn't replicate the improvements. The Zero's Sake engine already operated at thermal limits. There was no margin to reduce cooling drag without catastrophic failures. American aircraft had been over-engineered for safety. Japanese aircraft had been optimized for performance. Delaney's modifications had erased Japan's performance advantage by removing American conservatism. By December 1943, Delaney had been promoted to warrant officer and assigned to the Bureau of Aeronautics as senior technical advisor for cooling system optimization. The title meant a desk in Washington, meetings with engineers who'd initially dismissed him, and responsibility for expanding his modifications to other aircraft types. The Hellcat, the Thunderbolt, the Mustang, every American fighter would be evaluated for similar cooling system improvements. The work was exhausting and abstract, examining engineering drawings instead of touching metal, calculating heat transfer instead of feeling engine vibrations through his hands. He'd become what he'd never wanted to be, an administrator, a paper pusher, someone who influenced war through memorandums rather than wrenches. His wife, Catherine, had supported the transformation with bemused patience. "Michael, you're 40 years old. You've earned the right to work somewhere without malaria and Japanese bombers. Let younger men change spark plugs while you think about how to bring them home alive." But thinking about bringing them home meant remembering the ones who wouldn't come home. Lieutenant Hayes, Ensign Parker, Captain Morrison, who died in January when his modified Corsair's coolant line ruptured, spraying superheated glycol into the cockpit, blinding him before he could bail out. Each death was a data point in the larger calculation of acceptable losses versus operational effectiveness. The final statistical analysis, completed March 1944, quantified what Delaney had enabled. Hot rod modifications on Corsairs had improved squadron-level kill ratios by 143%. Fighter sweep effectiveness had increased by 67% due to improved cruise speeds allowing deeper penetration into enemy airspace. Combat losses had decreased by 34%, not because aircraft were tougher, but because they could disengage from unfavorable engagements that would have been fatal in standard configuration. The modifications had spread beyond Corsairs. Hellcats received similar cooling optimization, gaining 27 miles per hour top speed. Thunderbolts in Europe showed 43% improvement in climb rate after turbocharger cooling modifications based on Delaney's principles. The concept that American engineering had been too conservative, too cautious, too focused on peacetime reliability rather than wartime performance had become doctrine. Admiral Caldwell's letter arrived on April 8, 1944, typed on personal stationery rather than official Navy forms. Warrant Officer Delaney, the Navy Cross you received doesn't adequately acknowledge what you've accomplished. We don't have medals for mechanics who save hundreds of lives through thermodynamic optimization. But I want you to know that when historians write about American air superiority in the Pacific, your name should appear alongside Mitchell, Chennault, and Nimitz. You changed how we think about aircraft performance, and that change won battles that won wars. Thank you for being too stubborn to accept what engineers told you was impossible. The letter sits framed in the National Naval Aviation Museum, next to a cutaway display of a modified Corsair cooling system. Visitors walk past without understanding what they're seeing, the physical manifestation of an idea that hotter could be better, that safety margins could kill, that sometimes the greatest innovations came not from engineers with degrees, but from mechanics who understood that equations on paper meant nothing if they didn't work in the air. Delaney retired in 1946, returning to civilian aviation as a consultant for United Airlines. He spent 23 years optimizing piston engine cooling systems for commercial aircraft using principles he'd discovered in wartime desperation. His modifications to the DC-6 improved fuel efficiency by 11%, saving airlines millions in operating costs, while improving passenger safety through reduced engine failures. He never spoke publicly about the 17 pilots who died from his modifications. That guilt remained private, a weight he carried like the medals he kept in a drawer rather than displaying on walls. In 1973, dying from lung cancer caused by decades of breathing engine exhaust, he told his grandson, Engineering isn't about being right. It's about making choices. When every choice has costs, I chose to make aircraft faster, knowing some pilots would die from those modifications. More pilots would have died from slower aircraft. The mathematics were clear, but mathematics don't attend funerals. They don't write letters to widows. Remember that equations always balance, but consequences rarely do. Michael Francis Delaney died January 7th, 1974, at age 70. His obituary in the New York Times mentioned his Navy Cross, his work on commercial aviation, his 47 years of marriage to Catherine. It didn't mention that he'd fundamentally changed how America designed cooling systems for combat aircraft, that his innovations had been classified for 30 years, that the thermodynamic principles he'd discovered had eventually been applied to jet engines, rockets, and spacecraft. The memorial service at Arlington National Cemetery included a flyover by 4 F-14 Tomcats, aircraft whose cooling systems still incorporated principles Delaney had pioneered. The lead pilot executed a missing man's formation, pulling up into vertical climb that would have been impossible without thermal management optimization that traced its lineage directly to a mechanic who'd questioned why American fighters had to be so careful about keeping cool. Captain James Theodore Blackwood, retired, delivered the eulogy. He was 73 years old, walking with a cane from injuries sustained when his Corsair had been shot down over Rabaul in 1944. He'd survived because his aircraft had been fast enough to reach friendly territory after taking damage that would have doomed a slower fighter. Mike Delaney saved my life on August 14th, 1943, when he made my Corsair fly like hell with its tail on fire. He probably saved my life a dozen times after that. Every time speed made the difference between coming home and becoming a statistic. He understood something profound about engineering and war. Sometimes the safe choice is the dangerous one. Sometimes you have to accept heat to achieve speed, accept risk to enable survival. He made that choice for thousands of pilots who never knew his name. We're all here because he was right. The technical manual updates continued for decades after Delaney's death. The principles he'd established, thermal margin optimization, coolant chemistry enhancement, selective cooling reduction, became fundamental to aerospace engineering curriculum. Students at MIT and Caltech studied his field modifications as examples of empirical engineering outpacing theoretical predictions. The mechanic who'd been dismissed by doctors with advanced degrees became a case study in how practical knowledge sometimes revealed truths that pure mathematics missed. In 1998, the Smithsonian National Air and Space Museum acquired Corsair Bureau number 02158, Blackwood's personal aircraft, the first fighter to receive Delaney's modifications. The museum's restoration team discovered his original modification notes tucked inside the engine cowling, written in pencil on grease-stained paper. The notes showed calculations, crossouts, revisions, the messy reality of innovation that engineering reports sanitized into clean narratives. They preserved the notes behind glass, recognizing them as artifacts of a moment when one man's refusal to accept conventional wisdom had changed technological history. The cooling system modifications that Delaney pioneered eventually influenced designs far beyond aviation. Nuclear reactor cooling systems, automotive performance tuning, computer processor thermal management all incorporated principles he'd discovered. That optimal performance lived not at minimum temperatures, but at calculated thermal margins, where efficiency peaked. The mechanic, who'd never finished college, had contributed fundamental insights to thermodynamic engineering that doctoral candidates still studied 70 years later. But perhaps the most lasting legacy was philosophical rather than technical. Delaney had proven that expertise came from understanding systems, not just from credentials. That innovation often emerged from people closest to real-world problems. Mechanics who felt engine vibrations through their fingertips, pilots who knew when aircraft performance fell short of life and death requirements. The engineers with advanced degrees had designed cooling systems that satisfied theoretical requirements. The mechanic without formal education had designed cooling systems that kept pilots alive. The mathematics of survival never balanced cleanly. 17 deaths weighed against 847 lives saved created moral equations that refused to resolve into comfortable answers. For Michael Francis Delaney, those numbers were never just statistics. They were faces, names, and folded letters delivered to doorsteps. Each life saved meant a family spared the uniform knock on the door, but each life lost weighed on him personally, a reminder that even the noblest innovations carried shadows. He knew that decisions made on drafting tables and hangar floors could echo across continents and decades, long after the last rivet was set and the last flight log recorded. Delaney had understood that war allowed no option of perfect safety, only choices between imperfect alternatives. There were no solutions, only trade-offs. Every pound of armor added meant a pound less of fuel. Every inch of reinforced wing meant a fraction slower turn. He had chosen to make aircraft faster, believing that speed, above all, preserved life. Speed allowed pilots to escape enemy fighters, outrun flak bursts, and reach home bases rather than emergency fields. Speed, Delaney believed, bought survival. But he never forgot that it also demanded risks, measured in names, faces, and letters to families, risks borne by flesh, blood, and bone. He made that choice with eyes open, accepting responsibility for consequences both intended and accidental. He remembered every incident report involving Corsairs he helped modify. Some crashed because engines overheated at high altitude, others because control surfaces reacted unpredictably at extreme speeds. Each accident brought guilt, but also determination, to improve, to refine, to correct, rather than to retreat. War expected engineers to try, fail, and try again without pause. It demanded iteration in the face of tragedy. In the end, courage came in many forms. There was courage to fly into combat and trapped in glass and aluminum at 6,000 feet, praying instruments held and engines didn't quit. There was courage to innovate against institutional resistance, to stand up in briefing rooms against colonels and procurement officers and insist that established truth was wrong, that aircraft could be better, faster, safer. And then there was the quietest form of courage, the courage to live with the knowledge that every choice fit in war created casualties on moral balance sheets that never closed. Michael Francis Delaney had shown all three kinds of courage. He had flown test flights in planes nobody trusted yet, banking through dangerous stalls to feel how the wings shuddered and hearing bolts rattle where wings met fuselage. He had spent nights in workshops covered in engine grease, sketching modifications on scrap paper while the rest of the base slept. And later, long after the war ended, he had attended reunions where pilots approached him, some with gratitude for lives preserved, others with questions he could not fully answer about lives lost. The Corsairs that flew 50 miles per hour faster because of his work were monuments to what one mechanic's stubborn refusal to accept established truth had accomplished. Pilots credited that extra speed for outrunning Messerschmitts, for diving out of range of flak bursts, for returning from missions that should have ended in flame and smoke. The very same speed, however, sometimes pushed aircraft beyond their designed structural limits, causing failures that manuals never warned about. Velocity was both savior and executioner. Those machines carried more than just engines and fuel. They carried philosophy. They represented the belief that survival could be engineered, that fate could be altered through mathematics, metallurgy, and human ingenuity. But they also embodied the uncomfortable truth that every improvement asked a question: who would pay for it? Sometimes the answer came in the form of pilots standing proudly beside their planes. Sometimes it came in the form of silence, letters, and folded flags. Progress always extracted payment. Sometimes in ways the innovators spent lifetimes trying to reconcile. Delaney would never fully escape the weight of that truth. Long after the war, when he walked in through aviation museums and saw Corsairs suspended from ceilings like frozen birds in flight, he felt both pride and unease. He listened as guides told visitors about speed, altitude records, and combat victories. They spoke of performance metrics, not moral burdens. The aircraft had become clean, removed from the messy reality of decisions made under duress, with incomplete data and unpredictable outcomes. History remembered the machines. It remembered the victories, the speeds, the statistics, but it rarely remembered the people who built them, argued for them, doubted them, revised them, and quietly carried the costs of their existence. Delaney like many innovators of war, had walked a lonely line between necessity and consequence. He had chosen the path that saved the most lives, but not all lives. And that difference, that gap between most and all, was where his conscience lived. Some said the war made heroes out of men like him. Delaney knew better. War did not make heroes. It revealed the ones who were willing to carry the weight and still continue building, knowing the cost. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.